Yeah, so in case here,
I like got that whole thing and I was about to take the derivative of it and then I saw your little subtraction. I'm like, is there some kind of shortcut to this that I'm just being dumb and I don't know about? And
Wait, why would you take the derivative of it, Mason?
because because the partial molar volume is the derivative of the volume with respect to the, right there.
yeah.
Yeah,
This
yeah.
is effectively what we're looking at. So you have the delta V of mixing data. You fit this with a polynomial. The ideal function is just based on the ideal mixing properties. Taking the partial derivative gives you the partial volume. But then what I wanted to do is give you this function to plot, so that way you can see where does the deviation come from ideality for each component. Does that make sense?
So, but when you're taking the partial derivative with respect to ni,
So you can't do
Yeah.
x, right? So x of I is n's of I over summation of n's of I.
yeah. So you have to make that
But it's a
substitution.
binary mixture, so it's not that bad.
So you substitute that in, and then you would take the partial.
I have to double check my solutions though, but I believe that's how that.
And when you took that derivative, were there a bunch of like quotient rules and stuff in there you had to worry about from what you remember?
A bunch.
Because it seemed like every term was going to have a quotient rule in it the way that I had written it out.
I did not print out the solutions. I'd have to double check what the
Okay.
exact solution is. I think I might have just done it numerically.
Oh, really?
I'm not sure I actually did it analytically,
Oh.
but I have to double check.
Oh, so you don't actually have to.
Because am I asking for the function, or am I just asking you to plot it? I think I'm just asking you to plot it.
Okay, so we could just like take a difference.
I think I just did it numerically.
Oh, wow.
But I'm not 100%. I have to double check my solutions. But yeah, if I'm not asking for the function, I think you can just do it numerically if it's feasible to do it that way.
Okay.
So I guess I have another question about that. If you expand that out, then don't you have a partial molar V and a partial molar, or V for water and V for glycerol? So that's like, in my mind, that's like two unknowns, and then you have one equation. So I didn't know. I can write the way I'm thinking about it. It could just be wrong.
I'd have to check the details of the solutions for that specific question.
Yeah. That's what I was just kind of a little confused.
But the framework, so the partial molar volumes here, so a lot of terms will cancel out because they won't be a function of ni. But the terms that won't are the V over bars. Sorry, I'd have to look at the exact details of the solution to give you feedback.
Well, you can try it and see what happens.
But I believe I just did it numerically, from what I recall.
See, I for some reason think that delta V of mixing is equal to the sum of the xi's times the difference between the partial molar quantity of that I minus the, yeah. And so if I take all the information I know delta V, I know the delta x's because I just choose them. What I don't know, and then I know the ideal mixing V. But now there are two partial volumes that we don't know. It's water and glycerol. Are the two we don't know. So in my mind,
But you take this derivative twice. You do it once for each component.
Oh, and does that just give you?
But I think it should be the same form, you just swap the coefficients. So you'd only have to do, if you did it analytically, you'd only do it once, and then you'd swap the coefficients. Because it's a symmetric equation, it doesn't matter which.
Oh, so that gives you the two equations.
Yeah.
I see. Okay, that's where I was.
Yeah, so you have partial molar volume for the glycerol, partial molar volume for the water, and then you just repeat it.
Okay.
And that gives you those two expressions.
I see.
I suspect there's probably many ways to skin a cat on this one, I don't remember the exact.
No, but that makes sense. I was just like, we don't have enough equations. Where is the other one? Okay, makes sense.
We're not allowed to use a computer on the exam, right?
So, but that's an important piece of information, right? Because that's going to sort of be limiting the scope of problems.
Yeah.
So what that means, charts, lots of charts. TS diagrams, HS diagrams, PV diagrams, every sort of diagram that you can conceive of, is fair game, because that just means that all you got to do is put a dot on there with your pencil and look up all the properties.
So can we bring a ruler and, or? are we
That's
gonna
probably a
need
good
that?
idea.
Okay.
A ruler, probably a good idea.
A scale, sorry.
But when it comes to the charts, I'm typically extremely generous because I know it's a stressful time and there's time constraints. So when it comes to the exam and I give a chart, then I'm always very generous. And so, but if you can annotate your chart, that gives you a leg up, then I would recommend doing so, right? Because what I'll try and do my best to reverse engineer what you've done on it, and I'll be really flexible. So if I ask for what is the delta H of an expander, right, and I give you some sort of a TS diagram, let's say of water, kind of like the Rankine cycle on the homework, right? I'm not going to be looking for your answer to agree with my answer to 7 digits of precision, right? Plus or minus 10, 20% is usually acceptable if I can see all indications that you have used the chart appropriately, your energy balance is very explicitly written, your coefficients are very clear. But if I just see dots and a number, oof, you're not going to get the benefit of the doubt. Right? I want to see energy balances. I want to see entropy balances. I want to see, you know, the delta H of the expander, the delta H of the pump, right? That type of information. Or if it was refrigeration cycle, which I think what we have in the practice exam, right? Same exact idea. Follow the nomenclature that I provide in the chart, so it helps me to understand where you've done your energy balances, where you've done your entropy balances. If I ask you to do S-gen or delta S, it will most likely not be Q over T. I want to get everyone to stop doing that, right? S-gen is almost always done by delta S of system A, delta S of system B, delta S of total is A plus B. Yes?
So Q over T, is that term just like from heat loss to the surroundings? Like, is that what that term, like heat loss to an infinite body of?
Yeah, so if we look at the delta S, and this is great. So for the exam review, I do have some prepared material, but it's, I would say, fairly basic, so I'd much rather answer questions like this. So the key thing to remember about entropy is that this concept here, it's a little bit cyclic logic, but really this term is coming from the definition of what temperature is. Entropy is always concave or convex. Which one is it?
Concave.
Okay, so is that smiling or frowning? I'm really bad at this.
See, I'm so used to, I always say concave up or down.
It's like
and
the
then I
inside
know,
of the
like-
cave, so it's concave.
Yeah. So for me, it's always
Like the door
frowning.
of a cave.
Entropy is always sad. It's always frowning, right? So the way to think about this is you're kind of looking at the rate of change of entropy. So we could rewrite this differently, right? We could say ds is equal to q dot over t plus s gen. If we think about this reversibly here, right, we can get rid of that. With entropy, from the convex nature, no, concave nature, sorry about it, the lower the temperature, the more a fluid will gain entropy with a small change in temperature. The higher the temperature, the slower the rate goes. And so when you're transferring heat from one body to another body, unless they're at exactly the same temperature, right, the quantity of heat is going to be scaled by the temperature at which it's being transferred at, which basically means that if you transfer heat from a hot body to a cold body, right, you're always going to be generating more entropy in the cold body than you are losing in the hot body, and that's always going to be the case. Does that kind of help answer your question a little bit?
Yeah. So when would we actually use that term? Would it be like if you have a small body that's losing heat to a gigantic body whose temperature doesn't change no matter how much heat you put into it?
Yes, that would be a limiting case where you could apply this.
Okay.
But let's do an example here of a real system where that's virtually impossible to use. And I've given this question many times, and you had it on the homework. It's a fantastic question because it really, I think, highlights the concept of entropy generation for during a heat transfer process. Is a heat exchanger, right? So if I have a hot side and I have a cold side, right? Oops, that arrow is wrong. Let's go this way. Right, this is generating entropy. The only case that this is not generating entropy is if the hot is equal to the cold, right? So in this case here, this system A and this system B right? They have Q, same Q being transferred, but this one is at TA, and this one Q is at TB, assuming it's constant, right? So you have a mismatch in the temperatures, which means you have a mismatch in how much entropy is changing of the fluid. But in a real process, this temperature A and temperature B is a function of potentially the position in the tube and a function of time, whether or not this is a steady state or non-steady state operation. So if you wanted to hypothetically apply this notion right here, we could of course take ds and integrate it, but we would be following a path from, let's say, T1 to T2 of a volume element of fluid. Now here it gets a little bit more challenging. A volume element of fluid may be a delta Z slice that we are following as it travels through the system. But that's not going to have necessarily a homogeneous temperature distribution. So the only way to really apply this equation in the sense of finding out what the entropy generation is of the fluid itself is more or less coupling sort of a complex fluid dynamics calculation, or at least a fluid dynamics calculation, with a thermodynamics process, noting that how is the fluid here transferring energy to the fluid here, which is transferring energy to the fluid here, which is transferring energy to the wall, which is transferring energy to the wall, which is transferring energy here. That's not feasible for us to do with pen and paper on an exam. That is an approach, though, that is sort of the governing principles for heat transfer and mass transfer. This is exactly the way that you can rederive all those expressions. You can take it from an entropic approach. Same with momentum transfer, right? Everything goes back to thermodynamics. But in reality, we don't have to worry about that, because we can just make up an arbitrary system here, put a lasso around it, and then just keep track of the entropy coming in and out of each of these individual streams. I choose that approach.
And that's where the S-gen comes from. We just got
Correct.
S-gen from that.
Right.
Okay.
So the assumption could be, however, for example, and this is not necessarily going to be a 100% valid assumption, if we do an entropy balance on A, we could assume that the S-gen is equal to 0, for example. Basically, you're saying we're not generating any entropy internally in here, which we know is not fundamentally true. So there still would be some other nuance and subtleties and things like that.
Oh, so this was the problem where we had like delta S was the sum of the entropy of the streams coming in.
Right,
and out.
and that's almost always what we're going to do. So delta S of the system is going to be the change in entropy of A plus the change in entropy of B. In this case here, right, this is going to be the summation. Oops. And same right there, right? So this is going to be how much entropy is coming in, how much entropy leaving. Now, we generally will say that the ds is going to be equal to 0 for the whole process, meaning it's steady state. So that means the total entropy in here is going to be constant.
So they basically just balance each other out.
Yeah.
Yeah.
But this is something we did in the homework 1, I believe, was that problem. So if you go back to those solutions. Any other questions on homework, quiz, practice exam, general course materials?
Let's see.
Did you guys all get the number 2 solved?
We're working on it. It's close.
Random code problems. I got like a fourth of the way there.
So in general, this is for class and also for your thesis research. Most all of your time as a graduate student will be spent troubleshooting. If everything worked, you get your PhD in 6 months and you'd be out of here, no big deal. Because it turns out we're really bad at research when we first start off. So do everything in a manner that makes it easy to troubleshoot. That's my piece of advice for that particular problem. Same thing with your Excel spreadsheets. So I always build my spreadsheets following a set of rules, and those who've come to my office hours, I've told you about this, right? So in Excel spreadsheets, I never put a number in a cell unless that cell is the number. I only put equations with references to other cells. The only exception to that rule is unit conversions, right? And I also color code my sheet so I know which numbers are values from a table, which numbers are values that I'm interpreting, and what cells are calculations. So then when I look at my spreadsheet and this is my dumb color convention. Blue means I grabbed it from a table. So R is blue. Boltzmann constant is blue. The heat capacity correlation information, that's blue. Green would be what is the inlet temperature or the outlet temperature. Orange would be what is my delta S when I put in some particular equation. So then every time I look at my spreadsheet, I know exactly what I need to think about for every single cell that I click on. Did I type this equation in right? Did I put this number in right? Did I read this value from the table correctly? Saves me a tremendous amount of time thinking about it. And lots of comments, particularly units for comments in MATLAB and Python. That's what I do. But don't forget about numerical differentiation and numerical integration. Those are going to be your best friends, particularly when it comes to thermodynamics. You're not going to be able to get analytical solutions for most everything that we do in this class. Analytical solutions are out the window for any real practical problems, unless it's a simple equation of state. For real equation of state, no analytical solutions, only numerical. All right. So should I fall back to my content? If there's no other questions, so please interrupt me if you guys have any questions. So the starting point of the class of any real consequence, we're looking at chapters 3 and 4, energy, entropy balances, and I believe cycles was maybe chapter 5. Kind of lumped that all together. So the first law, and the second law, any problem that involves a process, I expect to see these. Otherwise, you're setting yourself up for failure. This is going to be your starting point for every process. The next step, right, of course in class, is obtaining these values for enthalpy and entropy. Or, in the case of a system that's closed, oftentimes internal energy, but not always internal energy. So, let's see if I can come up with a running list of types of questions. This is just sort of off the top of my head. Processes and balances. Give me an example of a question that I could ask that involves a process or a balance.
An expansion of a fluid.
Expansion of a fluid. Who created it?
Heat transfer.
Like heat exchanger,
Mixing process.
mixing, cycles, pumps, compressors, expanders, heat exchangers, piston cylinder devices, open systems, closed systems, those all fall into that category. Now, we cannot do anything with this because this doesn't tell us what are the values of enthalpy and entropy. In order to do that, we need to know how to do state changes. Now, in the case of steam, or any tables that I provide you, this information has already been done for you. Someone has gone into the laboratory, made experimental measurements, and they have come up with values of enthalpy and entropy that are accurate enough that we accept them as true. Now, this is something we didn't go over too much because it's really beaten into students really aggressively at the undergraduate level, right? H and S are arbitrary numbers. We don't care what that number is. We only care what the change of it is. And that's why so oftentimes we write all of our balance out in terms of ds, dh, du. Right? The absolute value of entropy is irrelevant. It only matters how it changes relative to a reference state. So in the case of steam tables, and the case of the table that you constructed on your homework last week, this is most generally 0.01 degrees Celsius U of the saturated liquid is equal to 0. That's a pretty standard reference state for steam tables. But to think about it this way, we don't actually care what the total energy is in a water molecule, right? Because in essence, it all depends on how you slice it. Do you care about the energy that it took to create every electron? Do you care about the energy it took to create every proton? Do you care about the energy that it took to create every neutron? Do you care about the energy that it took to heat that water up from absolute 0 to 300 degrees Kelvin? No. That would just make all of our tables be like 19 digits long, right? Because the nuclear energy is extremely high. So instead, we like to work with numbers that are close to 0 or 100 because it's easy to see. We don't like numbers that have a lot of decimal places. We don't like a lot of numbers that have a lot of commas. So we choose a reference state here. So now in the case of state changes, we have a couple of simple relationships. And this gets us to chapter 6. So I'm skipping over a lot of stuff here, particularly with processes. Oh, one thing that I want to say about processes is, let's say we do have some sort of a cycle. The implicit assumption with the cycle is that we're always going to be operating at steady state. And the way to think about how we're doing these balances is you can think about doing a balance on a unit operation specifically for a balance here. But we can also think about sort of a fuzzy volume element of fluid going through the system as well. And typically the fuzzy volume element of fluid is how we are doing state change calculations. Right? We have a sphere of some fluid, whether it's a gas or a liquid, and we're just magically transforming its temperature, pressure, or its density. That's how we perform state changes. You can also perform balances on the same systems, but in that case, it's a closed system, right? You're looking at how does the internal energy, for example, hypothetically change. Now, we can say with respect to time, but in reality, we control how quickly or slowly we do this. We can magically do it quickly, we can magically do it slowly, right? But in that case, if we're doing a closed system with an imaginary sphere across it, then we can transform and manipulate it any way we'd like to. And of course, we're going to do it reversibly because it makes our lives a lot easier. And that's why in all of our expressions of the combined first and second laws, we neglect the concept of entropy. Sorry, entropy generation. So the first thing that we did in chapter 6 to allow us to calculate state changes for real fluids was we combined the first and second law. So if we take a simple form for a closed system, again, a magical sphere or irregular surface that's containing all the fluid that we care about. We're not going to worry about any open or flowing systems. The change in internal energy is just the change in how much heat or work we're pulling or putting in or putting out of the system itself. Likewise, we are going to do all of the changes reversibly, because why not, right? We don't care about how we get to that endpoint, right? We just care about getting to that endpoint and determining how much is our entropy changing, how much is our internal energy changing. So if we make a couple of simplifications here, for work, right, we'll substitute in PV expansion work. And from there, we combine these two equations, right, basically solving for Q, the heat in and out of the system, and we get our combined first and second law expression. This is our starting point to allow us to calculate state changes, which allows us to solve our balances for the properties that we care about in the system. Namely, how much work can we extract out of a process? How much work does it take to change the properties of a system to some state that we care about? Or rather, heat, in a sense. Okay? Or in the case of entropy, entropy is most generally, we're using an entropy balance to choose a path where we know that we're not going to be generating any entropy. So delta S is going to be 0. That's usually our objective for the entropy balance. Now, we did a lot of different manipulations here. I'll go over a couple of the key ones. So if we invoke the Gibbs phase rule, noting that the universe is only constructed out of 3 variables for a single component system, and if we have an equation, we only need to provide 2 of those 3. So what we do is we write the total derivative for the change in internal energy as the summation of partial derivatives of each individual process variable that we're going to control. Now, of course, we're going to do this very cleverly. We're going to expand internal energy with respect to entropy and volume. Now, we know to do this because we know it comes up with a nice result. So that means the change in internal energy, in fact, this is going to be intrinsic property, so I'll put the underbar. That allows us to come up with thermodynamic identities. In this case here, temperature, we are defining as the change in internal energy with respect to changes in entropy at constant volume, and that pressure is defined as the negative change in internal energy with respect to its molar volume. This is the simpler of the two. Now, using this approach, plus all of the other properties of a thermodynamic system, how it's well behaved, there's no discontinuities, smooth and continuous, I mean, of course, save for phase changes, plus the definitions of enthalpy, of Gibbs free energy, and of Helmholtz energy. Right? We effectively created the entire foundation of thermodynamics. These functions and definitions are defined such that they produce useful conclusions. We can come up with a number of thermodynamic functions combining these properties that produce useless conclusions. But what we're teaching is the good derivations, the ones that actually produce useful, helpful information. That's why we're focusing on those ones. So then the challenge was to take all this information here and get it into properties that were only a function of temperature, pressure, and specific volume. So we did a lot of math. It wasn't too onerous, and I hope some of you went back and redid it yourself, because if you do it once, you really convince yourselves that, okay, yeah, this really makes sense. But a couple of the expressions that we were able to derive. And again, these are all on the equation sheet, so you don't have to worry about it. This will be provided. Everything you need will be provided. Every equation, every bit of thermodata, charts, absolutely everything. Now, I may overlook some things that I find basic, like delta H of an ideal gas, for example, or delta U of an ideal gas. Right? I might overlook those as things that we all sort of take as common knowledge. But the more complicated things that involve more remembering, I'll always provide that. This is intrinsic here. Okay. And likewise, for changes in enthalpy, right, so to calculate state changes, oh, I should have left some space down here. To calculate state changes, what we need then is simply an equation of state. So an equation of state relates between pressure, temperature, and specific volume. So if we take this information, we can calculate all of our partial derivatives, we can integrate this expression, and these can also be reworked for entropy as well. There's a number of different forms that we can rewrite entropy into. And actually, they're much more straightforward. So when it comes to an exam, if I were to ask you to do, a delta H for a real fluid or a delta U of a real fluid, it's a bit more tedious actually than the delta S. Everything in thermodynamics is just a little bit more straightforward when it comes to entropy. At least mathematically. Okay. How does everyone feel about this portion of the class? Now, this is a majority of what we've talked about And more recently, we've talked about multi-phase systems and multi-component systems. We're just kissing the surface of multi-component, multi-phase, so that's not going to be tested on the exam. So up through effectively chapter 8 is going to be fair game. Now we're up through chapter 6 right here, so we've only got 2 more chapters to go over, at least the general overview of how it flows and connects together. Any questions on state changes and balances? So with this information, right, being able to calculate the internal energy, the enthalpy, and the entropy using an equation of state plus heat capacity data is all that we need. And we can solve any real fluid process. Now the challenge then of thermodynamics is having an accurate equation of state, right? And that's something that people have spent decades working on, trying to improve. And finding a way to predict heat capacities. Then that's going to be one of the important origins of statistical mechanics, right? What is the underlying principles that determine how we know how much energy it takes to increase the kinetic energy of a molecule, which is the temperature as we know it. Back in the 1800s, we didn't know what temperature was. We didn't know what pressure was, at least from a molecular perspective or atomic theory perspective. That came as a result in the late 1800s and early 1900s, which seems really close to now. But we take it for granted because it's a really useful theory. All right, so with this information, we can basically solve any real chemical process that does not involve a phase change. Even if it does involve a phase change, right? The only thing is, we don't care, the energy balance doesn't care. The enthalpy of a liquid is different than the enthalpy of a vapor, but if you have access to a table and a chart, you're done. That table tells you everything you need to know to solve this process. If you don't have access to a table, that's when all of this information becomes important. Deal?
So, just
Yes.
a quick question. So like the first problem on the homework that's due today,
Yes.
we basically are using the entropy and enthalpy data, saying the entropy is constant, and then trying to like basically use a table to match things up. Right?
Correct.
So is
That would be
there
a good example of something I could ask on an exam.
Yeah. Is there an analogous procedure using like a real fluid to do that sort of thing?
That is a real fluid. Water.
Well, yes, but like if you don't have a table, if you only have an equation of state, is that something that you would ask, or
That would be a system of equations you'd have to solve then. It would be unpleasant.
yeah,
If you were applying this to a similar problem, you didn't have access to the tabulated data,
that's what I mean.
you could solve it in one go, but it would be a system, excuse me, a system of nonlinear expressions, I think.
Yeah. And it would be using those expressions.
Yes, yes, more or less. But you'd also have to combine it with the Clapeyron equation to get the heat of vaporization to do the second phase as well.
Yeah, that's right.
So non-trivial, right? So you would have to solve first for the vapor pressure,
Yeah.
to then differentiate the vapor pressure, which again, numerically, don't try and get that analytically, right? So in your homework problem number 2, once you plot the vapor pressure as a function of temperature, use a differencing scheme to get the gradient of it. Does everyone feel comfortable with that?
So what I'm asking about is like what we did on problem 2.
Yes.
Okay.
So then you're
Now it
building the
makes
chart.
sense.
Then you're building the chart.
Okay.
So now I did have another problem that I pulled away from this week's homework, so I didn't want to drown everyone. But that what you'll have to do on next assignment is you'll have to take your data that you've done on problem 2, and you'll have to then calculate the H, U, S. You'll build your own saturation table of the fluid using the equation of state. Right, and then you could basically use that. So in many ways, it's easier just to pre-calculate everything and then use the table to solve it. Because solving this in one go would be really challenging because you would have to know the vapor pressure to know the heat of vaporization. Well, you'd have to know the gradient of the vapor pressure to know the heat of vaporization. Makes it a bit more challenging. But in theory, it can all be done. Yes?
Can you please post the homework 2 solutions?
I did.
They're on there.
Quiz solutions, I guess that's.
Quiz, homework, and exam, quiz and homework are posted. I'll post the practice exam solutions today, but I believe they should be on there. You have access to them, Mason?
To the homework answers I do.
So in exam resources, that's where I posted the quiz and solutions, and I'll hand those back today. But then homework 2 should have been posted in the homework solutions folder also. That was on Monday, I got posted. All right, so I'm just gonna erase this one line right here. What is the next major type of problem that I can ask, following the progression.
Phase change.
Fugacity.
Yes, to all of those. Phase equilibrium, in which the fugacity of phase 1 is equal to the fugacity of phase 2, which is going to be our gateway into the axis. Now, there's some smaller topics we did, like, for example, the Clapeyron equation, right? So, if I were a student sitting in this classroom on Friday, and I saw a question discussing multiple phases, what is the equation that I should put down instinctually or habitually to start off my thought process?
Equal fugacities.
I already wrote it, equal fugacities. Fugacity of phase 1 is equal to the fugacity of phase 2. Now, in this particular exam, it's not necessarily going to be as prevalent as in subsequent ones, but when we go to multi-component, multi-phase, I want to see this on every single person's exam, bar none. Because this is going to be our starting point for every phase equilibrium calculation. Right? If it's liquid-liquid, we approximate the fugacity in a certain way. If it's liquid-vapor, we approximate the fugacity in a particular way. If it's solid-liquid, if it's solid-vapor, we all have approximations that we'll be talking about. Now, eventually, we'll simplify this down to Raoult's law, but in the case of a single-component system, this is our gateway here. Another option is that the delta G of vaporization or any sort of phase change is going to be equal to 0. That's how we got access to the Clapeyron equation, or the Clausius-Clapeyron equation, by substituting in the ideal gas law for the change in density of the fluid. But this is going to be our starting point right here. Now, the most important thing that we've talked about with single component phase equilibrium is how do we use an equation of state to give us that information. Remember, an equation of state is much more than just what is the pressure of the nitrogen in the tank. Right? That's the problem that you get as maybe an undergraduate, but it actually is the least useful application of an equation of state. However, that's how you benchmark it. So if your equation of state is accurate, it'll give you everything you need to know, not only state changes, but also phase equilibrium. And what we talked about this past week, which is not going to be on the exam, but with mixing rules, we can do multi-component and multi-phase at the same time. The PV diagram is the go-to for looking at phase equilibrium because due to the stability criteria of the universe, that entropy must be frowning, concave. We have a couple of key conclusions. Heat capacities must all be greater than 0, and that pressure and volume on an isothermic constant temperature, they must have a reciprocal relationship, meaning that if you decrease the volume, you must be increasing your pressure. So in the case of the ideal gas law, we get a radical shaped function. So in this case right here, this would be temperature is much, much greater than Tc, or pressure is approximately 0. So this is ideal gas type territory. Supercritical fluid. The ideal gas law, perfect for that. As you approach the critical point, you have deviations from this behavior. Near the critical point, you have a region where the slope is 0. That is how we define the critical point. Below the critical point, cubic equations of state adopt a very useful curvature. This information here is used for us to determine when the Gibbs free energy of this region cancels out with the Gibbs free energy of that region. That's how we get the delta G is equal to 0, which is the integral of V dP. Right? In that case, it was a really kind of a convoluted approach where we did the areas that way, but that's how we originally first started talking about the phase changes. Now we can do that for a single component system. As it turns out, defining a function called the fugacity is actually a little bit more convenient You know, when I see a fluid and I know it's at a certain pressure or temperature, I kind of have an understanding of what its properties are. But if someone were to tell me that the Gibbs free energy of a fluid is minus 50 kilojoules per mole, I don't really know what that means. So having the fugacity here is really just a mathematical convenience and sort of a comfort convenience and sort of reframing the phase equilibrium into useful units. When we get to multi-component systems, then it becomes critical that we assess the partial fugacity, because otherwise the Gibbs free energy, the partial Gibbs free energy diverges as you go to a diluted system. So it's a critical need for multi-component, multi-phase. So hopefully everyone is intimately aware with that procedure, because it should have been occupying a large fraction of your time based on the past few homework assignments. So we define the fugacity as a Gibbs departure function. So we can write, this is a common way to write this, the natural log of the fugacity coefficient, which is the fugacity normalized by the system pressure, is just equal to the Gibbs free energy of a real system minus the Gibbs free energy of an ideal gas system, right? This is the departure nature function of it. And then we just scale it by RT to make the units a little bit more convenient. And we tack on this pressure term. So it's really just a scaled way, but we could really define fugacity in a number of different ways. The most important contribution here is this departure function. The rest of this kind of just packs it up nicely in a convenient, easy to manipulate structure. Now, what you're working on right now, again, so hopefully I don't have to remind you of all of this, this is also equal to using an equation of state and this definition of the isothermal changes in fugacity. Right? So in Gibbs, you have minus SDT plus VDP. That goes to 0 if you're doing an isothermal process. So you can use an equation of state to calculate the fugacity. And in many ways, that's a pretty nice form. I would say compared to the garbage that we got to work with here for changes in internal energy and enthalpy, this is nice and pretty, in my book. This form, unfortunately, is not useful because this is right here is the ideal gas contribution, right? That's the minus the Gibbs of an ideal gas. Here is going to be from your real fluid. None of our equations of state are volume explicit, so it's not a particularly useful expression. So instead, what everyone else is working with is this form here. You know, you have Z. And again, this is also on the equation sheet, so you don't have to worry about it, other than how to apply the function. And what this has done is it has transformed our change from a pressure difference to a volume difference, which allows us to insert our pressure explicit cubic equations of state, which allows it more easily for us to take the differential. Now I'll just go over this really quickly because we're running low on time. I wanted to get through all the major topics. For the fugacity of a liquid, our best approximation is going to be equal to the fugacity of the saturated fluid multiplied by the Poynting correction Right, this accounts for the change in fugacity of a subcooled or compressed liquid. This is going to be important if we're dealing with liquid-liquid equilibrium. This is not necessarily going to be important until you reach in the order of tens of atmospheres pressures probably. And one way that you can check that is you can assume that this is incompressible. You can pull out the volume. You can integrate it, so basically this will turn into effectively an expression V over RT times by P minus P sat. You can evaluate this. It should have units. It should be unitless actually, but you can compare this sort of an order of magnitude estimate to what the fugacity is there and see how significant it is. It's not significant until you get to much higher pressures. Now we came up with a very similar Pointing correction, but for small systems, right? So if you have a really small droplet, the pressure on the inside is greater than the external pressure that is physically pushing on the droplet. So what we can do is we can substitute the internal pressure for that pressure, in which case the pressure internal to a small droplet due to surface tension effects is a function of surface tension or surface energy. We can introduce an additional pointing correction that has exactly the same functional form, or we can use the same pointing correction instead of integrating from P vaporization to the system pressure, you can integrate it to the internal pressure, or you can break this into two steps. P vapor to P to P internal, right? And the good news is that for multi-component systems, we sort of already covered it with the questions that were asked at the start of class. I wanted to go over one other quick example, just for maybe a minute or two, just to jog everyone's memory about what's actually happened during the mixing process. So the definitions, right, of a partial molar property and everything, that all stands true. We talked about that at the start. So let's look at, let's say, enthalpy of mixing. So this would be x1 equals 1, x2 equals 1. So this is pure component 2, this is pure component 1. This is the enthalpy of component 1, this is the enthalpy of component 2. Now we can either visualize it here that these two are not reference states, but we can also make it that these are reference states, so they're equal to 0. Right? We can think about it however we would like to. Now the real fluid itself, maybe endothermic or exothermic. Let's take an exothermic system. How do I know this is exothermic?
Because the energy of the system decreases when you mix it.
Right, so we have, in this case here, a negative delta H of mixing. Now, if I were to compare my initial state and final state, now in reality, right, fluid 2 is contributing enthalpy proportional to its mole fraction. So if we go to this point right here, we say, let's say x of 1 is that in the system. The initial enthalpy is going to be x of 1 times by enthalpy of 1. Right? In an unmixed system, that's how much enthalpy component 1 is contributing to the system, plus how much enthalpy component 2 is contributing to the system. And then the final system, right? My marker's dying on me here. Is just going to be whatever the enthalpy of the system is based on that real data. Final minus initial. Final is lower, initial is higher. That's all you have, a negative delta H of mixing. Now we can also think about this. Now the way that I've done it here is in a closed system. Right? Imagine I have a container with a membrane and I pull the membrane away. Right? That's effectively what's being done in a calorimeter. Now you can also think about this exactly the same way in a continuous steady state system. Math works out all exactly the same. You could have component 1, component 2, and leaving as a mixture. And then you could apply an energy balance. You'll come to exactly the same conclusion whether or not you think of this as a closed constant pressure system or an open continuously flowing system. Right? I think I erased my energy balance, right? But in a closed constant pressure system, we'll still use delta H. In an open steady state system, we'll still use delta H. Those two have exactly the same functional forms. The only difference is, do you consider it moles per second flowing in or just total number of moles in the closed system? But those are exactly the same equations. So you can think about mixing processes either in your head as a continuous steady state process or as a closed constant pressure process. Same thing. Now the reason why we do closed constant pressure is because the partial molar property definition mixes at constant temperature pressure. That's why. Now, we could reformulate everything for constant temperature and volume, but it's just easier to do it this way. All right. I think that wraps up most everything I wanted to talk about. Hopefully I covered any pressing questions. Yes,
Just a quick thing. So the mixture would be the final H,
correct.
and then the initials just.
Right, so instead of initial versus final, this would be out minus in.
Yeah.
So one thing, I have a meeting during what I told you all would be the help session time. When is a good time to have the help session? When do you guys have classes tomorrow?
I don't have any classes.
No classes tomorrow?
3 to 5.
So afternoon is no good. So midday is okay?
Yeah, middays would be good.
Okay, so 10 to noon? Is that acceptable for everyone?
1 to 3 would be good.
So 1 to 3 is when I cannot do, that was the original time. So who is not okay with 10 to noon?
Yeah, but it ends at 10:15, so.
Does it not work for anyone? Does 10 to noon not work? Does someone where it doesn't work for? Okay, I'll send that.
Till 10:30, but I can.
Okay, so we'll still have plenty of time that everyone can cycle through. All right, 10 to noon tomorrow. I'll send out an email to make it clear that we'll do the help session during then. And apart from that, please send me any email questions you may have about the exam. I try and make it fair, but remember, I'm testing on concepts, not rote memorization of the homework. Right, so if you can solve the problem, make sure you distill it down to its fundamental concepts. Process balances, state changes, phase equilibria, number 4, multi-component systems. It's one of those problems. All right, see ya.